Hi everyone, I'm Jamie and I'm a viola player in Year 9. And today I'm here to tell you about how maths makes music. So firstly, to understand my presentation, we must first understand the basis of music itself, fundamental note. They're the most ear-catching note you hear. So if I'm to play an A, you hear an A. And the higher the pitch I get on each string, the higher the frequency. Pretty self-explanatory, right? Sound only occurs because of vibrations through the air, whether that's from breath flowing through a tube or from a string, like this. Now with your naked eye, you might not have been able to see the vibrations of the string, but guess how many times that particular string vibrated in 1 second? Shout some numbers out at me.
9.
Okay, so 9, 20, okay, it's actually 440.
Oh, wow.
So, not very close. So, this particular string vibrated 440 times in that 1 second. And the reason it does that is because of the particular frequency, the length of that string and the thickness of that string. Whenever a note is played, sung, or even spoken, it creates an endless amount of other notes. These are called overtones and undertones. Think of the fundamental note as the tree. The overtones are like the leaves and the undertones are like the roots underneath. Take the note C in the second octave from the bottom of the piano, or 2 notes below middle C. In scientific language, this is called C2. The overtone series of that note is the C2, then C above that, then G, C, E, G, B flat, and so on. These get progressively softer as we go up. Most of the time, a highly trained ear can only hear 3 or 4 overtones. And we're all very lucky that they do get softer, or else whenever we'd hear that note, we'd hear this monstrosity. And same with the undertone series, except the overtone series is easier to hear. Another reason that we wouldn't want to hear that is because the higher we go up the overtone series, the more out of tune the overtones get in relationship to each other. And this is where the maths comes in. Do we all know what an interval is? Show of hands. Yep, for those of you who don't, it's the space between 2 notes. So if we look at this slide, we can see that each of the overtones of note C2 have a number underneath them. If we take overtone 2 or C2 and overtone 3 or C3, we can see that the relationship between them is 2 to 3, or their ratio. Now it stands to reason that because that's a perfect fifth, all perfect fifths should have a ratio of 2 to 3. Unfortunately, we've been foiled by the physics of sound there. If we look at overtones 9 and 13, their interval is a perfect fifth, but their ratio is 9 to 13, which simplifies down to 2 to 3.25. And it is this sort of discrepancy that puts the overtones out of tune higher up, but luckily the human ear isn't powerful enough to hear where it starts to go out of tune, so hooray for humanity. You may be wondering what determines whether a note is in or out of tune. Now the system that became increasingly dominant during the 17th century is the well or equal tempered system. The reason we use this system is because it's the most highly accurate and consistent system across all octaves. So if you were to play, for example, a C at the bottom of the piano and a C at the top of the piano, they will be in tune in relationship to each other. If we know that this A vibrates at 440 Hertz, then we can work out the A sharp or B flat above that using this formula. So if you multiply 440 by the quotient of 15.9 and 15, or by multiplying 440 by 1.05946, the resulting number is 466.16376, and that is the exact amount of times that this string will vibrate when I play this note. So in 1 second, that string vibrated 466.16376 times. Pretty cool. You can use that same formula to find any note in the equal tempered system, as long as you know the notes around it, of course. We now arrive at perhaps the most exciting and practical part of my presentation, harmonics. They are interesting wispy sounds created by lightly touching the string and not pressing it down all the way to the fingerboard. The light touch stops the vibration of the whole string but has equal parts vibrating. So if we look at this, imagine the fundamental pitch of that is in A equals 440. If I put my finger halfway on the string, it makes 880, and so on. So halfway down the string makes 880, which is an octave above. Then third way down the string makes an octave at a fifth above, 2 octaves. And that cycle keeps going on and on forever. And these are called natural harmonics. However, if I play a note by pushing down the string with my finger, which is this one's an E, if I now, which is different from the open string, I've changed the string length. If I now lightly touch the string at the distant perfect fourth above, I've made a note 2 octaves above the artificially made note. These are called artificial harmonics because I've changed the string length. And I've now broken the new string into quarters. And to find the frequency of that, you multiply the E by the amount of parts made 4. So you multiply that frequency E by 4. Harmonics are not only great because of the eerie and mysterious sound they make, but also because they can be used as a show-off technique. So we all know the national anthem. Now, if I play it with just natural and artificial harmonics, listen for that spooky and eerie, mysterious sound. But nobody wants to hear a whole piece like that. Not gonna lie, it's pretty annoying after a while. So I'll do a mix of both. So here's my variations on the national anthem, which I composed myself. I've taken a simple melody and I've written a virtuosic showpiece out of it with a diverse colour palette, thanks to maths and physics. I hope that I've now given you some insight into how maths makes music to describe sound. And I'd like to finish on a high note and also an incredibly cliche. Thank you for listening and enjoy the rest of your day.